All right, good morning, everyone. What we're looking at doing here first is going over any questions you have from yesterday, and then we're going to move on to a different region or area or set of ideas in this unit. Sure. So I'll just in just a second. So the idea here is that if you know how to solve what I'm going to call a linear trigonometric equation, then the only added thing that needs to be done if it's quadratic is to factor the quadratic to get linear. For example, if we take a look at, well, we'll just start off with 7a. 7a has 2 cosine squared of theta minus 3 cosine of theta plus 1. This equals to 0 is an important little thing. It's not a little thing, it's a big thing. It's important. So as long as you understand that cosine squared of theta means cosine of theta quantity squared, you're in kind of a familiar territory of Math 20-1 where you're factoring a quadratic. So you know that you have to put 2 cosine of theta and cosine of theta in the first 2 available openings in the binomials. The only 2 numbers that are going to multiply to give 1 are 1 and 1. And this is a particular question that doesn't require much thought, because if the constant term in the trinomial, in the quadratic trinomial, is positive, but the middle term is negative, these have to both be negative. And I have to go on an assumption at some point, and it's starting right about now, that you can factor that. I can't keep going back and explaining in lengthy detail how to factor something like that, because if we had to go back and spend a lot of time on all those previous skills, we would never get to the Math 30. So now what you would do is you would say that if cos theta minus 1 multiplied by 2 cos theta minus 1 equals 0, then either of these factors are equal to 0. And the reason for that is you're multiplying these 2 things together, so if one of them is 0, the product will be 0. And this takes me full circle back to where I started. Your goal is to create linear trigonometric equations. This is linear. We already know how to solve this. This is actually a Math 20 idea, where we rearrange here for cosine of theta, and we get cosine of theta equals 1/2. Myself, personally, I recognize 1/2 as an x coordinate on the unit circle in a couple of places. Specifically, on the unit circle, an x coordinate of 1/2 occurs here at this location for theta, and here at this location for theta. You don't have to be a unit circle thinker. I'll show you again how we can do it in another way. But, excuse me. All right, sorry for that interruption. So I was just going to go back and look to see what we want. We want radians here. So I would go on an assumption that if I drew this diagram for you, as it's not a beautiful diagram, but you should recognize that that first rotation angle is pi over 3, and the second rotation angle would be 1, 2, 3, 4, 5 pi over 3. And your other equation rearranged for cosine of theta would be cosine of theta equals 1. Well, and I should back up. I was going to mention this, and then the phone rang and I lost my train of thought. Who can explain to me why I was talking about the x coordinate here on this diagram being 1/2 in solving this equation on the left? Why was I looking at the x coordinate? Ian?
Cosine is x over y and the fraction is the x value.
Yes, except it's x over r.
Sorry.
You said y. I know you meant r. Yeah, so bottom line is on the unit circle, cosine is the x coordinate because r is 1 and cosine is x over 1. X over r, x over 1, it's the unit circle. Where is the x coordinate on the unit circle equal to 1 for the second equation? Well, there's only one location. We had this location, we had this location, and now we have this location, which is 0. So another solution would be 0. Looking at the domain here, just a minor quibble or note, we can include 0, but even though 2 pi takes us back to that location, we're not going to include 2 pi because it's lacking the equals part in the inequality next to the 2 pi. Do you catch my drift here? It just says less than 2 pi. It doesn't say less than or equal to. So your solutions here would be theta equals pi over 3, theta equals 5 pi over 3, and also theta equals 0. Now, what if you're not a unit circle thinker? That's okay. Because what you would do is you would use your calculator, and I'm not going to do it. You can do it yourself. Use your calculator to find a reference angle by taking inverse cos of 1/2, and you will get 60 degrees. So this is important. If you're going to use your calculator, you have to have your calculator in degree mode so you recognize the angle. And we get 60 degrees here. So when you get 60 degrees, then you say, oh, that's pi over 3. And you could find a reference angle here. And when you get the reference angle here, by going inverse cos of 1, you will get 0. And then you say, since cosine was positive, we're going to draw a reference angle of pi over 3 in quadrant 1 and quadrant 4 and quadrant 4 because those are the two quadrants where cosine is positive. And then you're going to say, well, what's this rotation angle? Pi over 3. What's this rotation angle? 5 pi over 3, which is what we had here. Then you could do the same thing here. Cosine was positive. So in which two quadrants is cosine positive, 1 or 4? This is a little weird, though, because if the rotation angle terminates in quadrant 1 and the reference angle is 0, it's not actually in quadrant 1. It's along the x-axis, which is why the other solution is theta equals 0. Okay, now, Reagan, you had a question. 3b. 3b. All right. So we're looking at this one. Now, I always hesitate in giving this one, but I'm giving this to you because some of you are in calculus right now, and some of you are in grade 11 and may take calculus next year. I think the likelihood that you would see this in a Math 30 exam, diploma or unit, or any exam is slim, but I feel as though I'm not just always teaching to the exam, although that's part of what I do. When you have 4 terms, very often you can factor by grouping. And factoring by grouping is a lost art, kind of. It's something that you're taught in grade 10 and then you push it to the side and you never really talk about it much anymore. Let me show you what we would do here. To factor this by grouping, and just because, Reagan, there are 4 terms, doesn't mean it's possible to factor by grouping. It is in this question. But if there are 4 terms, you want to try factoring by grouping. And that involves, first of all, zeroing the equation. Then what you're going to do is, out of the first pair, you're going to group these into 2 pairs. And I would really encourage you thinking of this pair as positive negative cos x minus 1. Okay, we're grouping a pair and another pair. That's why it's called grouping. Out of this first pair, I can factor out a 2 sine x. and be left with cosine of x plus 1. And then the idea behind factoring by grouping is now in the second pair, what we want to do is factor out of the second pair whatever we need to so that we're left with the same thing we were left with out of the first pair. We ultimately want these two things to be the same. And you may see why right now, and if you don't, you'll see why in a minute. So I have to factor -1 out. And now, this is something we talk a lot about in calculus, and I have a couple of calculus students here right now. When we started off on this line, there were 4 terms. One, 2, 3, 4. But what we have now are 2 terms. Terms are things that you're adding or subtracting from each other. So in the big scheme of things, what we now have are 2 terms. And we've arranged it. We've been clever about this. We've arranged it so that there's a factor of cos x plus 1 in each term. So what I have here is I have 2 sine x times this cos x plus 1 minus 1 times this cos x plus 1. So I have a common factor of cos x plus 1 that I can factor out. And when I factor out that cosine of x plus 1, I'm going to have left out of the first term 2 sine x, and then out of the second minus 1. And I'm not going to finish this question to completion. I'll get back to it in a second, but how many of you would have written these factors the other way around? Yeah, so for some reason, with some people, they just write it the other way around. You understand it doesn't matter. What we can do now, Reagan, is have cos x plus 1 equals 0 and 2 sine x minus 1 equals 0, giving us cosine of x equals -1. And by the way, we're using x as the rotation angle, but that doesn't mean x coordinate on the unit circle necessarily. And this becomes sine of x equals 1/2. And I would say that really, everybody, really, I don't even know that I would give you this equation on an exam to solve in this course, because this is a Math 20 equation, right? I'm not minimizing the importance of you being taught how to do it again in this course. You still need to be taught how to do it again, but it's really a Math 20 equation. The Math 30 is getting here. So I won't finish this, but are you a reference angle person or a unit circle person? Unit circle. So I would, looking at the unit circle, I would say that sine equals 1/2 here and here. And for video purposes, what I'm doing is I'm indicating with my arms in this location and this location is where sine is equal to 1/2. And cosine is equal to -1. Here. So you could say pi over 6, 5 pi over 6, and pi. If you're a unit circle kind of person, then you have to, or a reference angle kind of person, you have to work with your calculator to get those. Is that helpful? Okay. Any other questions? Go ahead, Shazmida. 1B. 1B? D. In the handout? Yeah. Okay. So I'm going to point out to everybody that this is a quadratic equation, and when you zero it, first of all, that root 3 is just, it's not root 3 cos x, it's root 3 times cos x. The cos x is not under the radical sign. I want to point out to you that this equation is missing a constant term. And this goes back to those 3 different quadratic equations that I talked about yesterday. In fact, I had set this up, I think, back here. Yeah. So when you do 1b, this quadratic equation has all 3 terms in the textbook, and you would factor it normally. When you look at 1d, it's missing a linear term, so all you would do is move this 4 over and take the square root and proceed. When it's missing, oh, I guess that's not missing a constant term. I thought this was 0. If it were 0, it's missing a constant term, and you still factor. So the question you're asking about is missing a constant term. We're still going to factor, but all we can do is factor out a common factor, which means I can factor out cosine of x and be left with 2 cosine of x minus root 3 equals 0. It's an important thing to remember because we get really caught up in factoring stuff like this where it's a full-blown factorization. You're going to have a binomial times a binomial at some point. That you forget you can still factor a common factor out. So does that first step make sense, Shesmaida? Okay. Now I can take each of those factors. One of the factors is cos of x. I can set it equal to 0. The other factor is 2 cos of x minus root 3 equals 0. When I rearrange, well, there's nothing to rearrange here. It's cosine of x equals 0. When I rearrange this equation for cos of x, I get cosine of x equals root 3 over 2. And again, I don't want to try to pressure students to do something that they're not capable of doing. But I think if you are capable, this is really simple at this point in time. Cosine of a rotation angle is the x-coordinate. Where is the x-coordinate positive? Well, it's positive in quadrant 1 and 4. And where is it root 3 over 2? You should know that this is at 1/2. You can kind of see it even though I didn't draw it perfectly. This is at 1/2 for a y-coordinate. And it's at root 3 over 2 for an x-coordinate. So it's this location and this location for cos of x equals root 3 over 2. If you wanted to use a reference angle approach, then you would take your calculator in degree mode and take the inverse cos of root 3 over 2, and you would be looking at 30 degrees on your calculator. So you would say the reference angle is pi over 6. Then you would say, Shesmaida, since the cosine is positive, it's pi over 6 in quadrant 1, and it's pi over 6 in quadrant 4. And then you could figure out the rotation angles. I don't want to muddy up the diagram much more, but remember the rotation angle would be from 0 counterclockwise to those positions. By the way, cosine of x is 0, happens here and here, because cosine refers to the x-coordinate, and the x-coordinate is 0 on the unit circle in those two places. If you find a reference angle, and I think this will be the last example we'll do before we move on today. If you find a reference angle, just do me a favor, everybody, find the reference angle from this equation. So you have to take the inverse cos of 0, and I want you to do it in degrees so that we recognize it. I believe you're going to get 90 degrees. Yes? So that has a reference angle of 90 degrees. Now this is awkward because when I say to you which quadrants is the terminal arm in, you look at whether the cosine is positive or negative, and positive or negative doesn't apply to 0. 0 is not positive and 0 is not negative. So unless you know something about the unit circle, this can get very confusing. I know that you could say, oh, well, let's imagine 0 is positive, and that means it's in quadrant 1 and 4. If it's in 1 with a reference of 90, then it's at the top. If it's in 4 with a reference of 90, it's at the bottom. It works, but 0 is not positive. 0 is as positive as it is negative. It's neither. Okay, so anyway. Well, any other questions? I don't want to rush us here. Ian?
For the textbook questions, 21D.
21D? Is this 21 here? Oh, yeah, it is. Okay, sorry. I had the 2 cut off there. 21D. So there are a couple of issues with this one. First of all, one of the issues is there's no linear term. The other issue is it's a reciprocal trig ratio of secant. And the third one is it's this goofy domain, negative pi to pi. But I would solve this by isolating the trigonometric ratio first, taking the square root of both sides, remembering, of course, that when you introduce a square root, it's plus or minus, and that leads us to 2 linear equations. One of the linear equations is secant of theta equals 2, and the other is secant of theta equals negative 2. So, your next step here, Ian, are you still with me? Okay, your next step here would be to write it as a primary trigonometric ratio, because whether you're going to use your calculator with a reference angle idea or the unit circle with xy coordinates as an idea, we have to think in terms of sine, cosine, not in terms of anything else. So since cosine and secant are reciprocals, I can write this as cosine of theta equals 1 over 2, and cosine of theta equals negative 1 over 2. Now, I'm actually really glad you asked about this. If you were a unit circle kind of person, since cosine is an x-coordinate, you're looking at where the x-coordinate is a half or negative a half. And what does that mean? It means, and listen very carefully to the language I use here, it means the locations are where x equals a half or negative a half, not the angles, the locations. When I look at x equals a half, remember this is 1, so x equals a half is halfway there. We're talking about this position and this position. These are both places where x is a half. Okay? So those are the 2 locations that identify solutions to the first equation on the left. Where is x negative a half? Well, it's up here and down here. These are the 2 locations that make cosine negative a half. Now, we have to look at the domain. The domain is from negative pi to positive pi, and I think it includes both of them. So this represents values of rotation angles that we can put for answers. So I'm going to start by going in this direction. This is 0. I'm going to go from 0 to pi and write down any angles that land in those positions. Well, pi over 3 does. So theta equals pi over 3. It's going to get a little messy because I'm putting all 4 on one picture. If I drew them all separately, it would be a little easier. 2 pi over 3 does. Does what? Sorry. 2 pi over 3 is an angle that is in between 0 and pi. But if I were to say 1, 2, 3, 4 pi over 3, 4 pi over 3 may be a solution to that equation, but 4 pi over 3 is not in the domain, so it's actually not a solution to this particular equation. So what I've done here now, Ian, is I have gone from 0 to here, and I've written down all of my answers. Now I'm going to go backwards. Now I'm going to say if I go in the other direction, this is negative pi over 3, and this is negative 2 pi over 3. So those are the 4 solutions. And I could get away with writing plus or minus pi over 3 and plus or minus 2 pi over 3. Okay. All right, we're going to move on now. And I'm going to break up our review in the unit here in a little bit of a weird way. We're going to do this lesson today, and then on Monday and Tuesday we're going to be reviewing all of the equations and trig ratios and maybe a little bit of review of this. And then on Wednesday we're going to finish the last lesson. I feel as though we need a break in the middle here to kind of review stuff. And what that's going to leave us with is, after we finish the last lesson on Wednesday of next week, it will leave us with 2 days in the week. We can have one more day for review, and then our exam is next Friday. So we're going to actually have 3 days for review here, because I know from experience that this is difficult for many students. And we want to make sure we're really solid for the exam, and also for the reason that the next unit is trigonometry as well. It's a continuation of this. So I know that a topic so nice we do it twice, and I apologize for that. I know that doesn't make many of you happy. So this is a lesson dealing with 5.1 and 5.2, which is graphing. I've changed my note structure. So this is not graphing trigonometric functions. It's graphing sine and cosine functions. We're not going to be looking at graphing the tangent function until the next unit. So we're looking at graphing sine functions and cosine functions. And if you look at the details of this at the bottom of the screen, what we're really talking about here is taking the graph of y equals sine of x and stretching it vertically and stretching it horizontally, or stretching it vertically and horizontally. The a's and the b's here are the same things that we were talking about since, I think, day 3 of this course. They have to do with reflections and stretches. And we're also talking about taking the graph of y equals cosine of x and performing those reflections and stretches. What we will do next Wednesday is throw in the shifts, the translations. So to begin with, we need to know what y equals sine of x looks like. And I want to talk briefly here about why this graph looks like what it looks like. But in the end, everybody, what is important is you know that y equals sine of x looks like this. Okay? So this is what's called a periodic function. It happens to have a y-intercept of 0, which means it passes through the origin. And we can add a few details to this. These things that I'm adding are not part of the graph. They're part of you understanding the features of the graph. There is a maximum value that this graph has, and there is a minimum value that this graph has. And these two dotted lines, again, are not part of the graph. They're part of you understanding how to draw these graphs. With sine of x, y equals sine of x, and if the x confuses you, use theta. I don't care. You could very easily, instead of having y equals sine of x, have y equals sine of theta and just label this axis as theta. Okay? Those two lines for y equals sine of x, and we will see for y equals cosine of x, confine the graph vertically. The graph wobbles up and down between having a maximum value of 1 and a minimum value of negative 1. And I want you to note that it repeats regularly. So if I take a look at the section of the graph from here to here, that section of the graph is identical to this section over here. It's identical to the section over here that continues. It's identical to the section over here that continues. This thing goes on and on forever, infinitely far to the right and infinitely far to the left. Another thing I want you to notice is that each of these, I can call it a cycle, and those of you that have, who has taken Physics 20 already? We talk about the cycle or the frequency of a wave. This is one complete wavelength for you physics people. But I want to point out to you that it contains 1, 2, 3, 4 pieces. This is going to be important later. A complete cycle has to contain 4 parts. In this case, the complete cycle is up, down, down, up. Okay? I also want you to notice that even though I don't really need to draw this, if I put a dotted line across the middle of this graph, that's what we would call the middle vertical position of the graph. It's midway between the maximum and minimum. We also see there are some x-intercepts here, and we'll get to that, but I want to go full circle now back to the beginning. I said I would explain why the graph looks like this, basically because if you take the unit circle, when you have a rotation angle of 0, and I'm showing with my arm here, so it's being lost on video, and I'm not going to try to duplicate it on video. The y-coordinate here is 0, which means the sine of 0 degrees or 0 radians is 0. By the time you get up to pi over 2, the y-coordinate has become 1, which means at pi over 2, the sine of theta is 1. As you go past pi over 2, the y-coordinate on the unit circle starts falling, and eventually when you get to pi radians, it's back to 0, and then when you get into quadrant 3, the sine is negative, and once you get into quadrant 4, it's still negative, but it's creeping back up to 0. You could make a table of values to explain this, but going, as I said, full circle back to the beginning, I said you just need to know that this is what it looks like. So one of the things I would say to you is you need to know that sine starts at the origin going up. But if you're ever stuck, and I want everybody to grab your calculator right now, and I don't want you to worry about what mode it's in. Okay? I want you to go y equals and enter sine of x. And then I want you to go zoom trig. There's a special trigonometric zoom setting. And there's a nice picture of what it looks like. Now, I happen to be in degrees. If I repeated that process, oh, there it is. If I repeated that process, I'm going to try to grab this calculator. I don't think I can. No, I can't. So I put in y equals sine x, and I happen to have been in degrees, but when I went zoom trig, it looks like that. If I repeated the process, but I happened to be in radians, and I go zoom trig, it's the same graph. Okay, so what I'm telling you is when you want to look at the graph of a trigonometric function, make sure you go zoom trig. What my calculator did on the left calculator is when I hit zoom trig, it looked at the mode and it said, oh, this person's in degrees, and they changed the window setting to go basically from negative 360 to 360. I don't know why it doesn't go negative 360 to 360. Negative 352.5 for some reason. If I went zoom trig when my calculator was in radians, my calculator looks at that mode and says, oh, this person's in radians. It's going to set the window setting to basically negative 2 pi to 2 pi. Okay? So it doesn't really matter which mode you're in. Let's take a look now at, I want to close out all these calculators. Could be a memory problem here. If we take a look at the features of the graph, what are the domain and range of this function? Well, the graph goes to negative infinity and positive infinity. Horizontally, it goes in every direction, so we can say x is any real number. What do we put for the range? Well, this is where those kind of guidelines come in handy. Because if you've drawn that horizontal line at 1 and the horizontal line at negative 1, you know that those are the, I don't know, vertical boundaries of the function. What are the intercepts of the graph? Well, I'll do the x-intercepts first. The x-intercepts, if you look at the graph, are at 0, and you have the graph in front of you, 0, pi, 2 pi, 3 pi, negative 2 pi, negative 3 pi. They're going to repeat every pi. So what we can say is they are multiples of pi where n is an integer. Basically, any place on the unit circle, you land in this position, which is traditionally called 0, or this position, which is traditionally called pi, you're going to have an x-intercept because the sign will be 0. The y-intercept is equal to 0. What are the maximum and minimum values of sine? Y max is 1. Y min is negative 1. And that's really tied, everybody, to the range. These are all features that you need to know. Now, there's something in mathematics called the period, and let's not worry about why we use k. We use k for the period, which is unfortunate because we also use k for a vertical translation. So you got to get over that. The period is how far horizontally it takes before it repeats. And if I go back to my graph, I'm saying to you how far horizontally is it for that green section, and it's 2 pi. This graph repeats every 2 pi. By the way, a complete period doesn't have to look like that. It has to have the 4 pieces. It could be down, down, up, up. And the distance from here to here is still 2 pi. It's just easier to see that it's 2 pi by looking at the green section. So the period of this function is 2 pi. The amplitude of a periodic function is how far it is from the middle of the graph to the maximum or the minimum. So in other words, this is what we call the amplitude, and we use capital A for the amplitude. This distance is the amplitude. The amplitude is 1 because the minimum to the middle, that distance is 1, and the middle to the top is 1. There's no direction with amplitude. Amplitude is how far it is, so the amplitude is 1. Let's take a look at cosine of x. Well, I'm not really going to explain this in any detail. What I will say is that when you look at 0 degrees or 0 radians on the unit circle, the cosine is 1. So it starts at 1. This is actually what we're going to call the start point when we get into this in detail next week. But it starts at 1. It still repeats in that same distance. This is still something that demonstrates the repetitive nature of this graph. It continues to do that thing over and over and over again. It's just that it starts out a little bit different than sine of x. So let's state the domain and range. Well, looking at this graph has a maximum of 1 and a minimum of -1 and a middle on the axis. So in terms of domain, range, max, min, all that stuff is going to be the same. The amplitude will be the same. The period will be the same. The only thing that's going to be different here are the intercepts. So looking at your graph, what is the domain? X is an element of any real number. What is the range? -1 to y, including -1, and y to 1, including 1. We'll do the intercepts now. The y-intercept looking at the graph is 1. Now the x-intercepts. The first x-intercept is pi over 2. Look at the graph. Why is that x-intercept pi over 2? Because cosine of pi over 2 is 0. The next intercept is 3 pi over 2. These intercepts here, these are separated by 180 degrees or pi. Because if you want to equate this to the unit circle, cosine is 0 at the top and the bottom of the unit circle, and those two locations are off by pi radians. With sine of x, we could have said the x-intercepts were just multiples of pi because one of them was 0. Here we have to say it's pi over 2 plus or minus multiples of pi in either direction. Where n is an element of the integer number set. Maximum and minimum, y max is 1, y min is -1. What is the period of the function? So how long does it take for this thing to repeat? It still repeats every 2 pi. This green section that I've highlighted is one complete period because it includes down, down, up, up. It includes those 4 pieces, and you need 4 pieces for a complete period. So the period is still 2 pi. And again, we use k for period. The amplitude is how far from the middle to the top or how far from the middle to the bottom, so the amplitude is 1. Now, that's the starting point for everything we're going to do today. We have a boatload of graphs we're going to look at here, and we may sketch some of them. We may not sketch some of them. We might do some of these on our graphing calculator. We might not even do some of them at all. We might just kind of, by the time we get near the end, know what the answers are. Okay, we're trying to develop, by looking at specific examples, some general rules. So the first is, what is 2 cos of x? Okay, just slow down. We don't need a graphing calculator for this. You know that cos of x starts at 1. Well, by the end of today, you'd better know that cos of x starts at 1. And it goes down, down, up, up, and it goes back to 1 here. If you wanted, and I don't really think you should be sketching what I'm about to sketch. If you wanted to sketch cos of x, then what you would do would be to put those vertical lines. You would take this and break it into 4 chunks, because you know that a complete cycle is 4 chunks. And you would say cosine starts here going down, so it's going to hit the x-axis here. It continues down. It's going to hit the lowest point here. It goes up. It's going to hit the x-axis here, and it goes up. And this is cos of x. You don't just draw it with straight lines. You draw curves. Curvy, 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 curvy. That's cos of x. Okay? What does the 2 in front of a function do? It stretches things vertically. So this isn't the graph we want. The graph we want is going to be stretched vertically by a factor of 2. That's all. That start point that was at 1 is going to be twice as great in terms of a distance away from the x-axis. It's going to start here going down, and it's going to arrive back at 2 pi over here. If it has to go from the first point that I've drawn, if it has to go down and then down, which is half of the period, it has to reach the lowest point halfway between those two. And it has to cross the midline halfway between those pairs of points. So this is what it will look like. If you wanted to draw that on the other side of the y-axis, that's fine. You should be aware that these continue in both directions, but that's enough for you to say what the domain, range, amplitude, and period are. The domain is any real number. And let's get something out of the way right now. There is nothing you can do to cosine or sine graphs to change that fact. The domain is any real number. What is the range? Negative 2 is less than or equal to y, which is less than or equal to 2. So now we have a maximum value of 2 and a minimum value of negative 2. I hope it's not lost on you that these two numbers at the bottom are 2's because there's a 2 in front of the cos. In other words, I won't go there yet. What is the amplitude? The amplitude is 2. What is the period? Since I hope it's also not lost on you that in terms of vertical stretches, A in this example is 2. Since A is a vertical stretch factor, it doesn't affect the horizontal behavior. So the period is still 2 pi. So if that's the case, well, let's take a look at the next one. Negative 3 sine x. We know that sine x starts here and goes up. Yes? If you look at the previous page, that's where sine starts there and it goes up. We know that sine would go up to 1 and down to negative 1, but this has a vertical stretch by a factor of 3. So what does that tell us? It tells us that there will be a maximum value of 3 and a minimum value of negative 3. And the middle of the graph is going to be here. But, instead of it starting at the origin going up, it has to start going down because it's been vertically reflected because there's a negative in front of the 3. This is pretty much all we need to get a picture of the graph, because we know it still has to go through one complete cycle in 2 pi radians because there's no horizontal stretch. It has to go, think about this for a second, it has to go, don't draw this, down, up, up, down. It has to have that overall shape, which means it has to intersect the x-axis here, and it has to be at a minimum halfway between 0 and pi, and a maximum halfway between pi and 2 pi. So what does this look like? Goes down, up, up, down. We could put arrowheads on there, but I'm not interested in that at all. You should be able to now write out domain, range, max, and min. Domain any real number. Range, -3 is less than or equal to y, less than or equal to 3. Amplitude 3, period 2 pi. And in fact, for what I believe are going to be at least the next two graphs, I don't even think we need to graph them. Remember, we're trying to develop general rules. So, well, I will graph a piece of the graph. If we take cos x, which has a maximum of 1 and a minimum of -1, and we stretch it horizontally by a factor of a third, because a is -3, then these two values for y will be 1/3 as great. Look, in the previous, let's go to A. In question A, the parameter A was 2. So the amplitude was 2, and the minimum was -2, and the maximum was +2. In question B, the parameter A was -3, but the negative didn't really play a role here. It reflected it, but it didn't play a role in what the range was or what the amplitude was. And this is what I was going to say earlier. And then I said, oh, not yet. This will always be your range today. Okay? Your amplitude will always be whatever the absolute value of A is. We shouldn't need to sketch this every time. And I can see that many of you have already filled this in. That means for this particular graph, and by the way, I would encourage you, if you want, to sketch them on your calculator later to confirm these if you're a little confused. But I think this is pretty straightforward. The domain will be any real number. The range will be -1/3 to +1/3. The amplitude is 1/3. The period is 2 pi. So now I'm going to give you guys about y equals 1/2 sine of x. I'll give you guys a minute or so to write in what the domain, range, amplitude, and period are. How many of you have already done it? Okay. Really what we're looking at here is the fact that a is equal to, is it 1/2? 1/2. You cannot ruin the domain of any real numbers for x. It's just impossible. The range, since it's 1/2, instead of going from -1 to 1, it will go -1/2 to 1/2. The amplitude, instead of it being from the middle up to the maximum, instead of that being 1, it's only going to be 1/2. The period, of course, is 2 pi. Good? Let's take a look at E. What does the sine of 2x look like? So now we're back to something new. First of all, I want you to note that B is 2, which means there's a horizontal stretch of 1/2. So I'm saying this is new because everything we've dealt with so far is A. If I take a look at sine of x, and this grid is here mainly for teaching purposes, not for you necessarily to construct an answer to the question, this is sine of x. If I take that and I stretch it horizontally by a factor of 1/2, then instead of going through a complete cycle in 2 pi, it's going to go through a complete cycle in pi. This will be the only thing that changes. Instead of going from this start point to this end point, the end point will now be here. So it is going to go up, down, down, up. This is what it would look like if you graphed it on your graphing calculator. I hope it's not a surprise. Oh, I went too high up there, didn't I? Have to really be creative on fixing this. Up, down, down, up. If I take a look at the domain, again, this thing continues forever in both directions. The range is going to be -1 to 1 because it's still an a value of 1, right? We have not stretched things vertically. The amplitude will be 1. And the period now is pi, and I want to point out to you, because this is going to be a huge time saver for us, that this period is 2 pi, the regular period, divided by b. If you take 2 pi and you divide it by b, which was 2, you get the new period of pi. Ian?
You divide it by the value of b or the vertical stretch factor?
No, I divide it by the value of b. And that eliminates the need for me to take the reciprocal of b to get a stretch factor. I'm dividing it by b, not the stretch factor. Cos of 3x. Well, if the graph normally, and let's jump to our calculator now. If the graph of cos of x repeats in 2 pi, or 360 degrees, then if I multiply x by 3, that stretches things horizontally by 1/3. It should repeat 1/3 the distance. Instead of 2 pi, it should be 2 pi over 3. So if I graph cos of 3x, it happens 3 times as often. And if it happens 3 times as often, the period will be 1/3 as great, which is 2 pi over 3. Wait, but b is 3. 2 pi over b. We can just take this whole stretch factor thing with trig functions and throw it in the bin. It doesn't matter. The period is 2 pi over b. The amplitude will be 1 because there's been no vertical stretch here. The range will be -1, less than y, less than or equal to 1. The domain is any real number. The domain of sine equals 1/3 x, the domain of y equals sine of 1/3 x would be any real number. The range would be the normal range because we haven't multiplied this by any a value other than 1. The amplitude would be 1. I want everybody to try to figure out what the period of this graph would be. If you look at the grid, there's kind of a hint there. It's going to be 6 pi. And there are 2 ways to think of this. And I'm not saying you have to think of it one way or the other. The regular period of sine is 2 pi. If I have a b value of 1/3, that stretches the graph by a factor of 3. And if I take 2 pi times 3, I get 6 pi. The other thing you can remember instead is this. And I'm going to throw absolute value signs on there just in case b is ever negative. The period here would be 2 pi divided by 1/3. Well, I'm going to multiply the top and the bottom of this by 3. And the 3's cancel on the bottom, and I'm left with 6 pi. You getting the idea here? What would the period of this graph be? We know the domain is any real number. We know the range is -1 to 1. We know the amplitude is 1. What would the period of this graph be? 4 pi, exactly. Which is either, let me write these in first, which is either 2 pi divided by 1/2 in terms of 2 pi over b, or it's 2 pi times the horizontal stretch factor of 2, which is 4 pi. How many of you think of this as a stretch thing to get 4 pi? How many of you are just going divided by b? You got to pick one or the other. Well, no, you have to pick whatever makes sense to you. So as a summary, and it, we still have examples to do here, but if you understand this, the examples will take about 3 minutes. They're not going to take long at all. As a summary, if we put a and b together, you'll notice I'm kind of crafty here. I went from talking about a sine x and y equals sine bx. I went from those two, and now I've got a and b together. It doesn't matter. The amplitude is the absolute value of a, and the period is 2 pi over the absolute value of b. This is what we've learned by looking at all of these graphs. And again, you could, if you wanted to, use your graphing calculator to explore this. So, what is the domain, what is the range, what is the amplitude, and what is the period of this? Well, the amplitude will be 3 because the parameter a is 3 and the amplitude is the absolute value of a. So it's the absolute value of 3, which is 3. The period, well, we've learned that the period is 2 pi over b. So this will be 2 pi over 2, which is pi. What is the domain? X is any real number. What is the range? Well, if the amplitude is 3, it's going to go from -3 for y to +3 for y. Really, when you boil down this lesson, I could have just told you this at the beginning, but I think it's important you understand what these graphs look like. Take a minute and write out the domain, range, amplitude, and period here. Put your hand up and then down if you've already done so. Okay. So I'll just give you a minute. Don't look up here and just copy what I have. Do it on your own. Pretty simple. What's an equation of a sine function that has an amplitude of 4 and a period of 90 degrees? Now, if this is the only other thing we need to talk about briefly here, if the period is 360 over b, and I'm using 360 instead of 2 pi, when you rearrange this, you get b equals 360 over the period. So b is 4. Take 360 divided by 90, you get 4. This period is 90 degrees. So the value of b is 360 over 90, which is 4. There we go. Why does this question say determine an equation? The reason is we could do this. That's an equation whose amplitude is 4 and period is 90 degrees. I could put a negative in front of the other 4. All right, I'll give you a minute here to write out an equation. This was for part A. I'll give you a minute here to write out an equation for part B. And again, how many of you have it already? Little more thought here because of the decimal. I would convert the decimal to a fraction. Although, I guess you could just leave it as 0.5, right? But you need to figure out what b is. And I have to admit that sometimes I do think of stretches. That if the regular period is 2 pi and it becomes 6 pi, I've stretched things by a factor of 3, which means b is a third. Or you could say b is 2 pi over the period, which is 2 pi over 6 pi, but that's a third. One final question here. The graph is a cosine function. We have to find the equation of this cosine function. So the amplitude is 3. What's the period? If you look up here, one complete cycle is up, up, down, down. The period is pi. The period is 1/2 of what it normally is, which means that we need to put 2x here. But what I have written at the top is wrong. It needs a little tweak. Why is that equation, y equals 3 cos of 2x, wrong? And by the way, I just noticed, does your graph say 2 pi, 2 pi? It should say 2 pi, 3 pi. This should be 3 pi. I will have to edit that. What's wrong with this function in terms of an equation? Arden? Yeah, we don't always have to. We should, but sometimes I see it without the brackets. That's not really the big deal. Yeah, Madison? The 3 should be negative because cosine always starts at the top going down, but this graph starts at the bottom going up. There must be a vertical reflection here. Cosine has a start at the top on its way down. This one is the opposite. So there's the answer to the question. What this boils down to, everybody, really is this summary that I believe is at the top of the page we're on right now. That's what this boils down to. So a collection of practice problems on page 233. We do not need to spend time graphing things. You want to step beyond that so you can say, oh, this is the period, this is the domain, this is the range, this is the max, this is the min, etc. So on Monday, we're going to take a break away from new material. We're going to spend a couple days reviewing everything we've done so far. And then we're going to continue that on Tuesday. Wednesday, we move on. Okay? But I do want you to get this stuff done, get some practice done for Monday. Okay?